Hey, so today's teardown is a bit impromptu. So what I have here is a slightly out of whack kilowatt. As you can see, there's actually, my line voltage is 113 and this is reading 135. And then actually, this is also like a minor update on the power meter project. Here is the power meter as it currently stands. You can see this is just a piece of paper. But yeah, so here's the, I bought these cases. There's a company called Polycase that makes these very nice plug pack enclosures. And then you can, this is actually not the final layout. I've modified it a bit subsequently. But you can kind of see you've got current shunts, and there's a fuse here, and link power supply, ATX Mega, there's the CS5490 power supply monitoring IC, and then there is a that header here. So this is an NRF24L01 Plus, and then this just kind of sits right there. So right now, I'm in the, kind of trying to decide whether I want to, one of my contracts with one of the companies I've been working for is kind of coming to a close, and I'm trying to decide whether I want to look for other work or to try and actually throw a bunch of hours into this, to kind of decide whether or not I really want to push forward on the power meter project or not. I mean, it looks like it's very viable. The BOM cost for this is about $8 to $10. The case is $4, and so I think we could probably get it totally together, assembled maybe for 20 bucks, maybe go for a $25 sale price. There's a specific brand of snap-in outlets that fits here, and then you can, it's a very, I like it a lot. It's smaller than I thought it would be. I mean, you can kind of see it's significantly less tall than a kilowatt, though it is much thicker. Unfortunately, they don't have any less deep casings. But anyways, what I figured I'd do today is, the line voltage is drifting around. What I will do today is reverse engineer the kilowatt a little bit. These are interesting. I've taken a kilowatt apart before, but it was a while ago, and I have some pictures, but I never really pulled the circuit from it. Really marvelously safe outlet strip. Don't ask how that happened. I definitely noticed that these things are inclined to fail. This one had been sitting with my server in my server closet plugged into it, and after about 3 months of being sitting there plugged in, the display turns off, and it becomes unresponsive. Actually, I thought it was completely broken, and then I plugged it in again, and you saw it was out of cal. So whatever, however these things are built internally, their long-term reliability is kind of crap. Don't know what caused that. This is definitely, I don't think this is the one I took apart, but definitely check out that juicy soldering job right there. That is high quality. This definitely looks like the one I took apart before. This is not the only one. So it looks like, as near as I can tell, they hand solder the various tines. Actually, while I'm here. Alright. So as you can obviously see, they have a, the power supply is done with a plain old-fashioned, just an RC, a capacitive reactive dropper. And then you've got, so here's your current shunt. And then I don't actually know how they're measuring line voltage. I should actually spend some time reverse engineering this board. So you can see that this terminal here runs to this end of the current shunt, and then it runs there and there. And then there is there's a trace here. So you can see we have kind of Kelvin connections. The power comes in on this side, and then the current's tapped off there. The ground, this entire circuit is mains connected. It's also not isolated. And then you can see that here, so the AC mains runs to this capacitor. And then it looks like it also, okay, yeah, so then it goes, I think it runs under the middle of the capacitor to this end of the fuse. and then it runs through the fuse to one terminal of the capacitor. And then it looks like they just have 120 volts right here. Oh no, this is going to be neutral, I think. Clip leads, that's what you get for $5 on Amazon. So that is directly connected. Directly connected. So, yeah, so this pin here is directly connected to that tab. Whereas, how the hell do they have creepage? So, I gotta switch lenses. This is nuts. So look here. So, this pad here is directly connected to one of the terminals on the line, and this trace is directly connected to the other. How the hell do they get these proper creepage distance there? Look at that, they've got freaking 120 volts. I mean, hell, right here, they've got 120 volts across this little tiny notch. How is that safe? I'm gonna have to... What the fuck? Also, wow, look at this soldering job close up. This is a fucking production... I mean, wow. Just wow. This is production. Supposedly. You know, if you have one of these, pop the back off and tell me if it's as horrible as this, because this is nuts. Look at this, it's disgusting. It's not even cleaned. Yeah, so I'm going to definitely sit down and try and reverse this properly, I think. Actually, what I am going to do is, because this is coming apart permanently, I am going to scribe a line there. And then just come in here with some skizzers and just go snip. So here is the front panel. You can see there's a few passive components on there. Alright, so now, one thing of interest you can see here is they've got a whole bunch of footprints for a whole bunch of different capacitor types. You can also see that this is designed from the ground up for 120 volts. You know, there is no way in hell this shit would pass EU clearance of any sort. So it looks like this whole board must have been soldered in 2 steps, because these solder joints are far nicer than the other ones. So my bet about how this works is that it's wave soldered for all of the parts except the big tabs, and then somebody comes in and hand solders the rest. It's a very labor-intensive assembly process. Yeah, so I was correct. So AC mains there, one's under there. That is not a lot of creepage. You know, man, I've been fretting about some of the creepage distances on the board, this board, and you know, I mean, like, I've been worrying about, you know, creepage around here and so forth, and man, these are actually PCB cutouts just for higher voltage, and I actually brought this cutout down through here as well. But, you know, ignore some of the messy designators. That's actually a mechanical dimension on the layer that won't actually show up on the board. This is designed for the Oshpark process, which doesn't allow plated slots. So what I've done is that these will just be folded over onto the board and soldered down to those pads, or I'll probably put a bit of wire there instead. And I've thickened up these traces because that needs to handle 15 amps. That won't work. But anyways, yeah, man, this is kind of ghastly, to be honest. But yeah, so terminal 1 and terminal 2. I mean, it's just bananas. I mean, it's insane. I mean, this trace here is directly connected to 120 volts through this fuse, and it runs right next to that pad there, which is on the current shunt. You know, I mean, which also means that they have to be bringing 120 volts over to this board. That's nuts. Wow. Just wow. I'm surprised this shit doesn't catch fire. Wish I had a high pot tester. It'd be interesting to see where this thing fails. Probably fail at like 300 volts. Anyways, so you can see we completely single-sided board. 4.194304 megahertz crystal. Weird ass numbers. Little 1/8 watts. Big half watts. I wonder, I bet these are part of the current measuring, and then we have a couple transistors. What are these transistors? It's a 2N3904 78L05. No kidding. Another 3904. Another 3904. Man, those are just like ultra shite jelly bean transistors. All right, let me change back lenses wise. Here's the cap on the reactor dropper. It's 0.47 mic, 300 volts, X1 rated, which is, so it's a proper cap. It's pretty compact. I'm surprised how small this is, to be honest. But here's this board. You can see the jumpers, this big thing, another diode transistors. So here's our board. And one of the things you can see that's immediately interesting is that look at the buttons. They don't use carbon-doped silicone pads like most of them do. There's actually a completely metal disc installed on there, which I think is interesting. Another thing is you also have to realize that this button membrane is all that's insulating you from 120 volts. So that may be why they do it this way, because they don't want any carbon doping. Well, I guess the carbon dope pads are normally glued on, but I guess they want to make sure, maintain the insulative nature of this, or maybe they just actually care about a decent number of, a switch life with regard to, button press cycles. Just put this on backwards. So here's our actual board, and you can see that it is pretty sparse. Everything of interest is under here, and we have 2 chips and a cob, because cobs are for assholes. But anyways, so one of the nice things you might notice is menu up, down, enter, output, which is quite nice of them actually. So the chips on here are, this is an LM2902, which if I remember correctly is just a very inexpensive quad op amp. This over here is an ATMLH936, which I believe fairly strongly is an Eeprom. And then there's the cob. So whatever is in here, the ADCs have to be in here. So what I'm actually going to do is I'm going to reverse the circuitry on here because I want to see how they're doing it. So first of all, let's start with this. So, I mean, I don't see any particular problems with the way they're doing this, aside from their hideously undernourished creepage distances. So you've got your current shunt comes in here. You've got one lead tapping off of the ground. Yeah, so you have your lead tapping off of the neutral for measuring the current. And then it's also worth noting that oh no, they're not. They're just ignoring. So, and then you have what looks to be a trace that runs all the way back right to the pin, presumably for getting your voltage reference, because that's very narrow. So the critical thing is, so these 2 pins, pins 3 and 4, are heavy. traces are much thicker than all the other ones. So then this is your current, and then these two are your, and the critical thing is that, you know, these people are insane because they are, you know, basically they're running the two AC line voltages immediately adjacent to each other. I mean, this is neutral and this is hot. I mean, that's just bananas. You know, the creepage distance is that. Just this between those two pins. I mean, it's kind of nuts. Anyways, grab another page. I have all these. I have a huge pile of 11 by 17 printouts that I did from my you know, for work, that are now sitting around. Output. Man, they are exploiting the fact that 78L05 doesn't need output capacitors. So they don't have any. So this goes out. There's a resistor pulling it up. There's a series resistor. And then this goes into another transistor's base. It's also grounded. And then this is the output fed into the logic. So this, as near as I can tell, must be some sort of zero crossing detection something. I wonder why they felt the need for this I mean, I guess maybe they had to invert it twice, because this goes high, this goes low. This goes high, it pulls that down, which means this goes high. Yeah, so it's a non-inverting transistor buffer. But I mean, maybe their chip, weird. Because if this transistor is saturated enough to pull this down to the threshold voltage of turning this off, this voltage here must be swinging enough to easily trip logic. So I mean, this has to either be on or off. It's not like they're running this in a partially conductive and they needed an additional transistor for more gain. They're just inverting it again. I wonder why they're bothering to spend the money on that extra transistor. So this should produce... Oh, I know what's going on, I think. So, I bet this is a Zener. So what I think they've got here is this is probably like 2.5 volts. I'm confusing the auto ranging shenanigans on that. I gotta go to the 789. Six volts. That ain't right. Oh. Of course, it's tied to V+. So is this another power supply rail? So let's see, this terminal here should be... Oh, whoops, I am applying 20 volts now. I think I'm over voltaging it a little bit. So I forgot I was set the things to produce a lot more voltage. So that is indeed a Zener. Oops, sorry, I gotta keep it on camera. So the output over here should be 6 volts, yeah. I wonder why they have these two separate rails. Actually, I bet one of these is used for the analog stuff, maybe. Where did my dental pick go? There it is. Assuming this is a standard. Huh. Yeah, okay, so it looks like they have a separate analog and digital supply. That's very interesting. I guess the analog supply probably draws very little power. You know, so they can just get away with their funky transistor Zener shenanigans. I thought they might have been using it for some sort of bizarro split rails. So we have this, which comes out to 6.1 volts. Okay, I just went off and did some other stuff while it was daylight here. So we just went off, what I just did is I basically just figured out the power regulation system, and now I'm going to look at the rest of this. The first thing is this is an L2902. Okay, so this is using the completely standard op-amp, quad op-amp package. I'm kind of surprised the 2902 is a quad. I would think that would be a 2904, but, you know, whatever. So, this is kind of additionally confused because you can see all these buttons. The traces for all the buttons are kind of in the way. It's a little messy, but that's better. Alright, so here's kind of the power supply section and the board. So this is... So there's the part of the schematic. So obviously you can see I'm kind of going multi-sheet here just because I can't draw it that small. I'm betting that's ground. So we have a standard differential amplifier here. So it looks like they've got, basically this function, it's a differentiator. They're just high passing the current signal. I wonder why they don't do that to the... So why do they feel the need to high pass the current signal but not the voltage signal? I don't understand. Alright. Yeah, so they've got like a funky voltage divider thing going on here where the voltage at this node changes depending on which of the buttons you press. Same thing here. It looks like they probably had two I/O lines left and they needed to fit 5 buttons on it, so they did this kind of little shenanigan. But yeah, this is the entire, I mean, this is all of the analog stuff on here at all. Yeah, so I mean, there's the entire analog section except for whatever the cob is. I mean, that's everything. Incidentally, the line sync, this input here, which is basically just, so you have your AC waveform, and you have like the basically 0 volts along the middle, and the line sync output is just going to be high when it's high, like so. You ignore my crappy drawings. Because what they're doing is basically they're just saying that when this voltage here is positive, this goes high. Well, actually, when it's positive, this goes high, which means this goes low. Yeah, so when it's When that's high, that's high. I wonder why they bothered with this transistor shenanigan again. But yeah, I mean, it's extremely simple. I mean, they're using, everything is integrated into the one chip. You know, this little voltage reference thing here is interesting. I mean, you can kind of, there's also basically a capacitor here, which is across the one, there's a capacitor immediately proximate to the, it's right next to the 2902. But, you know, basically there's one capacitor there, and I wonder, you know, it's just as minimal as it gets. I wonder what the microprocessor in here is. I mean, you can see it's got a crystal, and then they've got, these are the loading crystals for the capacitor. There's a series resistor in series with one of the beepers. There's a lot of jumpers. Carries power over here, power over there, you know. It's a, you know, as you can see, it's single layer. Here's the line sync trace runs up here between these pads here and then into the micro. So there you go. It's interesting that they decided to include a separate Eeprom, which is actually just sitting right here. It's, you know, so I guess I don't know what the microprocessor, you know, in the cob is, but it must be so inexpensive it doesn't even have a built-in Eeprom, which I think, you know, so it's probably one of those Chinese, you know, 5 cents on the dollar parts. But yeah, there you go. I hope you found this kind of interesting. It took me quite a while to extract the schematic just because it's very fine pitch. Actually, why don't I give a close-up of the board just for a second. So here's the actual board. Some of this, like you can see the come here, you. This flux mess here is not mine. This is from the original assembly. This is mine. You can see this is where I lifted these pads when pulling the 2902 off. But you can see here's, you know, basically this trace here runs to that pin there and then to here. And if we flip over, that's a resistor, and I believe that's 5 volts. Interestingly enough, it's referenced to the digital 5 volt, not the analog 5 volts. Actually, so, oh no, sorry, it's not that resistor, it's this resistor. What is that other resistor? Oh yeah, that's that other resistor. So this goes to here, which is referenced, this is the digital 5 volts. This other resistor here is part of the series input on the current section, I believe. But you can see these are the these resistors here are the networks for decoding the buttons as an analog voltage. These are just jumpers. Here's the Eeprom. The traces are kind of insane. I mean, you can see that one of the Eeprom traces runs up here right into the micro. The other one runs up, pull-up resistor apparently, through this jumper, down here, under all these parts, and then up here, finally. Actually, it runs through here, down there, down, underneath this cap, up here, and then there. It's, I guess it's what you get when you have one layer, and, yeah. I guess they must have had used the hardware Eeprom module or something, or hardware I2C module. Here's the power section. These are the resistors that form the inverter for the line. Here's a close-up of this spectacularly bad soldering job again. I'm just kind of amazed by that. You know, I mean, I guess the reason they're being so cavalier with their creepage distance is because everything is, you know, after this fuse. You know, this 200 milliamp fuse. So I guess they're just assuming that if anything happens, this fuse will blow. Which seems like bad practice, but, you know, what do I know? There's the big series resistor, brown, black, brown, gold, black? Oh, brown, black, brown, that's 101 times 0.1, so that's 10.1 ohms. Huh. And there's the series diode. So the cap charges up through this. So basically the cap charges up through this resistor, or excuse me, diode, and discharges through that resistor again. You remember the schematic. When the voltage swings low, current flows through here and charges that cap, and then when it swings high, it dumps out into the regulator. So I guess they expect much bigger pulse currents through this diode than this one, because this diode is physically larger. Go figure. Anyways, there you go. Oh yeah, here's the you can see the little filed notch. So this little notch here is the tuning for the current shunt, which is just a giant chunk of brass rod bent into a loop. I don't know what that logo is. So I wonder, you know, considering their complete cavalierness about creepage here, I wonder why they bothered here. I guess I would bet that they're much more concerned about leakage to ground than they are about leakage between the, you know, hot and neutral, which seems kind of counterintuitive to me, but I don't know. Also, oh, I think those are for, the 3 holes there are for alignment pins, because this actually, oh no, I think they're for retaining screws. So because this slides in, and then actually, not only are there, oh wait, no, I guess this slides. That's as in as it goes. So it maybe at some point there was putting screws in there, but that seems, I mean, I think they're just support posts. Because I don't know how you'd put screws in there without having to worry about short, you know, electrical connection across the screws. But I wonder why they bothered putting those holes. Well, actually, where is the back? No. So here's the back, and you can actually see that when this sits into the, so when this sits in there, you can see these plastic tines actually poke up to provide even more, you know, insulation. Oh yeah, it does turn out locator pins do sit into those holes, so never mind. They're just extremely small. You can kind of see, so what happens is when you're plugging and unplugging, all of the force of the plugging, you know, which wants to push this board out, is taken up by these posts, which is why they're, I guess, why they're there. Okay.